Right. Hi, everyone, and hello, maybe from the past to anybody joining us from YouTube, perhaps the distant past. I suppose this will be still relevant in 100 years. We'll see. So I'm going to cover the second topic today, that is observables. By the way, I am Chandler Bennett and currently a postdoc here at Oak Ridge National Lab. My email is provided there if there's any questions after this talk, or if there's any issues with the subsequent lab material that we'll cover. And also let me remind everyone that all of my materials, as well as the materials you've seen so far, can be accessed at this GitHub website. Okay, so let's jump in. Here's a brief outline of what I'd like to cover in this topic. So we've spent a lot of time discussing calculating energies with QMCPACK and also variances, which gives us an idea about the quality of the wave function. But we have access actually to other quantities beyond the total energies. And I'd like to discuss briefly what those various quantities are and how to calculate them. We'll do a pretty deep dive into the density estimator. It's a good quantity that we can cover in a pretty brief amount of time. And we'll talk about how the density, so I call it estimator, but I use this interchangeably also with observable. But the charge density we'll calculate in the VMC case, and we'll see first how that looks. And then we'll move on to the DMC case, and there's an added complication when using a observable that does not commute with the Hamiltonian in DMC, and this introduces what's known as a mixed estimator bias, and we'll go into detail about what that is and various ways to minimize that. And then after a Q&A, we'll go over the lab material. I'd like to show you or walk you through the calculation of the charge density of the water molecule. And as I guess Paul already advertised, look forward to seeing you next week, as we'll be seeing some interesting QMC research presentations from guest lecturers. Okay, so let's jump into the quantities that QMCPACK can access beyond just total energies. I want to first point out that you actually, in some of your labs, already have access to quantities beyond the total energy and beyond the variance. So if you have a look at any scalar.dat file that has been produced from your QMC runs, and say perform a head on that file, you will notice that not only does QMCPACK record the local energy and also the square of the local energy per block. This is what each one of these rows are. It represents a block. It also records other quantities related to the energy. So for instance, it records what's known as a local potential. This is every term in the Hamiltonian that's local. It records the kinetic energy. It also records the electron-electron repulsion, the ion-ion repulsion, and it goes on also to record the local EC, what's known as the local ECP, or that's what the label is here anyway. And this is all the local components within an ECP. Recall that Lubos just showed us that an ECP is comprised of a local piece and a non-local piece. And so this is the associated energy for the local terms. And then similarly, this is the non-local terms of the ECP, specifically their energy. There's some information about the blocks and also the acceptance ratio. And we can obtain means and error bars from these quantities pretty easily. Also with the QMC tool, as Jaron introduced in week 3. And what you can do to get the means and the errors is simply running QMCA. Hopefully you can see this on the scalar.dat file, and it will give you a full list of the quantities, their labels, their means, and their error bars. And you can also, if you wanted to just access a subset, you can actually supply any of these labels to the -Q flag that Jaron introduced us to. Okay, well, what if we want to access things beyond the energies? Well, QMCPACK is also capable of doing that, and it actually can calculate a rather broad range of observables or estimators, and not just the total energy. For instance, Josh introduced us to the Chiesa kinetic energy correction last week. That's one example. To the right, I'm showing some results from recent publications where QMCPACK was used to calculate the momentum distribution. In addition, there's been some recent works where QMCPACK has been used to calculate density and the spin density. The density is just the total charge density of the system, and then spin density separates the density in terms of an up component and a down component. Okay, and there's others as well. So QMCPACK can calculate what is known as the energy density. This is analogous to the density matrix, but instead of calculating say a number density or occupation numbers, it does these with energy quantities. QMCPACK can also calculate the one-body density matrix. It can also get at the spherically averaged pair correlation function. And so this essentially quantifies how the particles are effectively located relative to one another. QMCPACK can be used to calculate the static structure factor. Josh actually showed us that last week. And we can calculate forces and others. And so for a more detailed list, more comprehensive list, as well as formal definitions and implementation details and how to run these estimators, I would suggest you look at the following references here. So we have the online documentation of QMCPACK. That's a good first choice. And then we also have QMCPACK's citation paper and a recent QMCPACK paper that covered recent advances in QMCPACK. Let me go over briefly a few notes on QMCPACK estimators. So to calculate them, modifications actually to the QMCPACK inputs are generally minor, easy, intuitive, and user-friendly. And so I'm giving an example of 4 estimators here. And notice that a lot of these, let me first mention that so in the input, I provide these XML elements, and I'm calculating density, spin density, the pair correlation estimator, and the static structure factor estimator. And most of these are just sort of one-liners that fit into the QMCPACK input. So that makes the practitioner's life very easy. Let me also note that the estimators can be evaluated during all chained QMC runs. So for instance, if you had a VMC run followed by multiple DMCs, you wanted to do a time step extrapolation, for instance, or you wanted to speed up imaginary time evolution, you might chain runs in this way, and QMCPACK can be run in such a way that the estimators are calculated at each one of these instances. But it doesn't have to be run that way. So we can also specify things such that only specific QMC sections evaluate the estimator if we want it. For instance, if we wanted it only for the VMC. And the online documentation outlines precisely how this latter case can be specified. Another note is that generally the estimators are not available for optimizations or even needed. Recall that we're mostly interested in the energies and the variance when we're performing an optimization. And so if you were interested in your optimal, your estimator with your optimal wave function, you would first do your sort of vanilla optimization of, say, your Jastrow parameters. And then you would just follow that up with a VMC calculation with the relevant, or the relevant estimators or the rest estimators that you're interested in, you would have them turned on. So let's do a deep dive into one of these guys, namely the density estimator. And let me first cover what this looks like in the VMC case. Okay, so to calculate the charge density, or just the density, we use the particle number density operator, and it's again given formally by the following equation. And essentially what this operator does is, for a point R, it gives you a count of the number of electrons that are at the point R. So you notice with the delta function here, once an electron, say Ri, is sitting at R, the function turns on or is non-zero. In practice, of course, QMCPACK can't just doesn't record for every single point in space. So QMCPACK uses a finite histogram grid, which the user will define. And then it averages the number of particles in each grid cell over, say, an ensemble of walkers distributed as psi t squared. We'll call this as VMC. And this, it gives it access to the charge density N at all grid cells. So let me show you precisely what that looks like for a specific cell. Let's call it C. And so you notice that we're performing an average over psi t. And then we're integrating within the cell volume, cell C, and we're using this particle number density operator. And what that translates into for whenever we perform the Monte Carlo simulation is essentially you're looping over all of your samples. Say you have M samples, you're taking an average, and you're recording the number of samples, the number of electrons in the cell C, essentially. Let me note that this is easily extended to what is known as the spin density. And so you would do the exact same procedure in VMC, except now you do a separate, you do a separate histogram for up and down electrons separately. And then this allows you to generate their respective densities. Okay. Now, how about for the DMC case? Let's do the following. However, let's first step back and look at how the energy is evaluated in DMC. And so recall that in DMC, we're performing an imaginary time projection. And so if we take the limit that the imaginary time goes to infinity and apply the projection operator or the time evolution operator onto an initial wave function psi t, this will evolve in principle to the ground state. And so what this first line essentially is that we're averaging the Hamiltonian over the ground state wave function. Okay, but recall that we can't really get access directly to the ground state wave function in DMC, so we have to modify things a little bit. So notice that these projection operators, of course, commute with the Hamiltonian. So what we can do for the second step is take this projector here and move it all the way through to the first part of the, we can move it all the way through to here, okay? And what this leads us to is this. And so we have an imaginary time projection of psi t on the left, h still sandwiched in between, and psi of t on the right. And that looks like this, essentially, what I just said. And we call this the mixed estimator. And we've done everything, everything we've done to this point is perfectly legal. So this represents exactly the energy of our system. Okay, and so practice, if we write this in integral form, we'll see that we have the desired property, namely we are averaging the local energy over a distribution psi 0 times psi t, which is what DMC provides us with. Now, the problem with observables in general is that not all of them, of course, commute with the Hamiltonian. And so we're already stopped. We can't move past this first step to get to an expression like this. Okay, so if we, however, evaluate an observable, say O, that does not commute with the Hamiltonian in the same way that we normally do the energy, there's going to be a linear error incurred. And so this is, I don't show it here, but it's quite easy to do. So what I'm suggesting is that if you calculate the observable in this way, you're going to get an error. And you can show that it's linear by replacing psi t here with, say, psi of 0 plus some function, call it delta, that represents the error. And what you can quickly show after a couple of steps is you'll get the form of the expectation value that we want, plus a term that's linear in the difference between psi of 0 and psi of t. And so the result does indeed depend on the quality of our trial wave function. And so to improve upon this in practice, we actually use a combination of the mixed estimator, say from DMC, and a variational estimator, say from VMC. And that looks like the following. And you can actually do the exact same exercise with this expression. If you replace all of these psi t's with psi of 0 plus delta and massage the equations around a little bit, you'll notice that you get the quantity that we want, plus a term that's the next term is actually quadratic in the difference. So that's an improvement, and it's generally something that we do when we calculate estimators. And let me also give a brief comment. If you're looking at the scalar quantities as well that I showed at the beginning, any of those quantities that do not commute with the Hamiltonian, if you're wanting to quote their DMC results, you should use this extrapolated estimator to arrive at their estimates. So in addition to this extrapolated estimator, however, we also have an alternate approach. And this gets around the problem of using the wrong distribution, essentially. And this is known as forward walking. And it enables one to sample the pure distribution psi of 0. This is beyond the scope of this talk, though the method is implemented in QMCPACK, and the details can be found in the online manual. Some further notes. So when calculating the density for systems with open boundaries, the user must specify the cell that will be used to evaluate the density. And it's best to center the molecule in the desired cell, of course, because you don't want significant portions of the density outside of your simulation sort of box. And so it's easier to center it in the cell, and generally you'll pick up more density, of course, as opposed to being, say, at the edge. And for periodic boundaries, generally the supercell is used by default. And as I mentioned just a second ago, be sure that when you are estimating any observable, make sure you keep track of whether or not it commutes with a Hamiltonian, because if it does not, then at a bare minimum, you should be using the extrapolated estimates of that quantity. Okay, and I can take questions now.
Thanks, Chandler. I'll give people a moment to type any questions they have. I think just to echo what you were saying about measuring the charge density of molecules just now, we measure the charge density in the sort of positive octant defined by the lattice vectors. So if you put a molecule centered on the origin, the charge density will get clipped. So putting the molecule at sort of half is the standard way to do things. I think probably everybody's done that once. So here's a question from Samuel Green. How do the errors in these estimators depend on the finite time step in DMC? Should one apply time step extrapolation to them?
You should certainly converge it. That's going to be different depending on what estimator you're looking at, and it's going to be generally different from the extrapolation for the energy. But that is something that you need to be concerned about and make sure you're either, is something you need to make sure is converged.
So I'll ask one question and then we'll move on. So Johnny, you mentioned there's this list of observables, but they're not on by default. And could you explain a little bit about the cost of evaluating these different observables? I mean, they're not zero cost.
Right, so we don't want to turn them on by default because some of them can be quite expensive depending on which ones you're turning on, and especially if you're turning on a lot of them at once. So we generally leave that to the user to specify which ones they want turned on. I'm not prepared to talk about specific scalings, but there is a wide range of scalings depending on what estimator is used. And so it is something that you need to consider whenever you're running these.
All right, there's a more technical question now, but I'm going to refer that over to the Slack. And John, I suggest you continue.
Okay, well, let's jump into now a brief lab that shows how to calculate, say, the charge density of the water molecule. Okay, so before we get going, as always, please use git pull with inside the QMCPACK Workshop 2021 directory on your VirtualBox, and also within the QMCPACK apps directory. And to give an overview of what we're going to do next, we're going to first generate the orbitals and the wave function using PySCF and QMCPACK, for water, that is. And in step 2, we're going to calculate and store the VMC and DMC charge density. In step 3, we're going to be introduced to a new tool that we haven't seen before called QDens, and we can use this tool to generate, say, an XSF file for visualization in a program like Vesta, but it can actually produce other formats like the charge car from, sorry, I forget the name of the program now, but various other formats can also be outputs. And then finally, we'll introduce one additional tool called QDens Radial. And this will allow us to estimate quantities based off of the density, such as the atomic occupations of, say, the oxygen atom. And we'll also show briefly how to do an extrapolated estimate and also resample to get error bars for that quantity. Okay, so first, step 1, let me first note that all of these materials are located within the week 6 observables directory, and the files used for this simulation are contained within this directory here. The workflow is titled H2O workflow.py. And let me just jump into what is going on in the workflow. So first, we bring in the CCECPs that Gani just introduced us to a moment ago. And then we define our physical system based on an XYZ file that contains the structure of our molecule. In addition, we give the appropriate Z effectives for each of the atoms. All right, and then we go on to perform a Hartree-Fock calculation for the molecule. And this is similar to what we've seen before. We're using PySCF. And then once that converges, you should, if it's worked correctly, you should see an energy close to mine that's down here. And once you have that, you'll go on to convert the orbitals such that QMCPACK can read them with the following generate convert for QMC function. Okay, and then we'll follow up the converter step with a simple two-body Jastrow optimization. And you can specify two-body as we've seen before just by saying J2 equals 2, or J2 equals true. I've given a fairly large cutoff for the Jastrow. I'm telling the code that I want to do an optimization and use the one shift only minimization method. And these are pretty standard settings. And I want to incorporate the particle positions and orbitals from the previous steps. And in my case, when I run this, I see that Hartree-Fock leads to a wave function with a variance that with a variance to energy ratio that's roughly 0.02 Hartree. Okay, now that we have an optimized wave function, we can go on to calculate the estimator of choice, which is here the density. And so what I'm performing here is a three-step calculation. I'm performing a VMC first, and then I'm performing a brief DMC with a large time step, and then I'm following that with a longer VMC with a large, smaller production time step. And this is should be very similar to what we've seen from previous labs, except now we're calling this estimator variable here. And we can provide, so I'm not sure how familiar you are with Python, but these brackets generally denote a list, and you can actually provide a list of estimators. Here we're just providing the density, and within the density function, I specify a few parameters. So let me cover these first. These xmin, xmax, ymin, ymax, and so on define the boundaries of the box that we want to calculate the density in. And then we can also provide this delta, which is in relative units to your box. And so providing for each x, y, and z direction. And so 0.02 would then represent, would correspond to 50 grid cells in each direction. In order for you to be able to call this density function and supply it to this estimators variable, be sure to do the following import, which I show above. Okay, and so after the QMC runs are completed, the density for each block will be located in the stat.h5 files. Okay, and then now we're motivated to use the QDens tool for two reasons. So first, we want to average the density over the blocks. And I guess I didn't put a 2 here, but we do want to do the average, but then we want to also write to a format that's suitable for, say, visualization or analysis. And so how is this done? Well, before you start to run QDens, what you want to do is run QMCA first on your VMC and your DMC results to get the equilibration and the autocorrelation links, because QDens will be able to use those when it's constructing its average. And so after you have those quantities, I'm showing an example here where the call to QDens is made for the VMC, which corresponds to series 0. And what we tell the tool is that we want it to output an XSF file. This will be used later for visualization in Vesta. We provide the number of equilibration blocks. There'll be some number that we determine from QMCA, and we want to throw those away, and we'll throw them away from the QDens as well. We provide a reblocking factor, which allows us to get rid of auto correlation errors. And then it gives, we need to give the tool an example DMC input so it can have access to the structure. It has the ability to plot, but we're not going to do that now. So we provide this flag no plots, and then we give it the corresponding stat.h5 file. And then the same is done for the DMC with the appropriate equilibration and the autocorrelation links given. And what both of these end up giving you are 3 files in the density case. They'll give you the mean of the density, which is this density underscore q.xsf. But then it also keeps track of the standard deviation, and will give you the mean plus the standard deviation and the mean minus the standard deviation recorded in these files. And the exact same is given for the DMC. Okay, so what can we do now? Well, you can take those as they are. For instance, well, first, you can take those as they are and run them, visualize them in Vesta. And if you're in your virtual box, you can just type all capital letters Vesta, and that will open up this GUI. And then from here, you can easily import, say, the mean of your DMC density, which was this file here. And so you'll simply go to File, Open, and then point it to that file, and it will, the initial image that you'll see is something like this. It'll give you some generic kind of isosurface. And there's various settings that you can play around with. You can change the isosurface ISO value. You can look at contours and so on. And for all of it, and for various capabilities within Vesta, I suggest you look at the following reference here, the Vesta manual. Okay, so that's nice, but can we do anything else? So step 4, let me introduce now the QDens radial tool. And now we'll actually use, we'll get an estimate for, say, atomic occupations on the atoms in water. And so once QDens has given us these density.xsf files, we use this QDens radial tool now to calculate the populations. And how does this work? And so what the tool does is, given a set of species and say cutoff radii in angstroms, what the tool will do is perform a radial average or an angular average around the atomic site that you specified, and record the radial density up to your cutoff radius. And you can choose the radial density to be either non-cumulative or cumulative, that is integrated. And so the integrated cumulative radial density would then be something that you could relate to the occupation of the atom. And so how do we run the tool? So what you can do is, first, if you're interested in plotting, say, the DMC non-cumulative radial density of oxygen, you just type QDens radial. You tell it that you want to plot with this -p. You specify your species here. I'm just saying oxygen O, but you can provide here a list. I could have easily said O, comma H. And then you give a cutoff radii, either a global one like I've done here, or you can also give a list, and it will use the corresponding radius for the corresponding species. And then you provide the XSF file, and that will give you a nice plot like this. And so this is the non-cumulative DMC density around the oxygen molecule or atom. If we want to look at the cumulative radial density, all we have to do is to put on this, turn on this -C flag, and that produces the same here, except now cumulative. Okay. We can also print the cumulative value at the cutoff radius. So this is generally used to estimate, say, the population. And so if you run, this is the exact same command, I think, as before. If you run this and look at the output of your terminal, you'll see that this is actually recorded for you. So this tells us that the cumulative value of oxygen at the cutoff 1 is equal to roughly 6.55. And this is consistent with the intuition as we expect the oxygen to pull charge away from the hydrogen atoms, of course. And we can also, with this same tool, get a estimate of get an extrapolated estimate because we're thinking about mixed estimator bias. And so for this, we can simply give, in addition to the DMC XSF, we just tell it that we also have a VMC XSF density lying around. And it by default will combine the two together to give us an extrapolated estimate. And so notice that this did change a little bit. Okay, getting close to the end here, I wanted to quickly show how to do now an error bar. Recall that in QMC, any quantity that isn't given an error bar is effectively meaningless. And so what we can do to get an estimate of the error bar is to do this resampling approach. And so what we can use is the error bars from these XSF files that were given from QDens, and we can draw samples from a Gaussian distribution with standard deviation that matches the error bar. And we can do this for every grid point. And then once we have these various samples, we can calculate occupations based on this resample data, and then do a mean and a standard deviation to get the error bar pretty easily. And the code actually will do this for us as well. And so all you have to do is provide a similar command as before. You can tell it that you want to run a certain number of samples for the resampling. You also have to provide it with the error file here. And then you can provide, again, the DMC density. And if you keep track of your terminal outputs, it will show you that the error bars are being accumulated. You're using 20 samples. And after that finishes, sometimes that can be slow, depending on the number of samples you use. But once it finishes, it will give you the value. This is, recall, the value we saw before and the error bar. And this is, before moving on, this is something else that you'll want to make sure you're converged to. So if you use just a few samples, your error bar likely will not be accurate. So you want to use more and more samples until you're convinced or until you see that your error bar is not moving anymore. Okay, some brief notes. The same tools, QDens and QDens radial, can also be used for periodic systems and for the spin density estimator. And you can use them to perform twist averaging when creating the converted files. In addition, for spin densities, QDens will generate a collection of XSF files containing up, down, up plus down, and up minus down densities. And these can also be easily visualized in Vesta. And in addition, QDens radial can then be used to, say, estimate populations again for the atoms just by using the up plus down density, but you can also analogously get access to the magnetic moments by running the tool on the up minus down density. And that's all I have here, and I'm happy to take questions.
Thanks very much, Chandler. So please, everyone, if you have any additional questions, please put them in the chat. While we're waiting, Chandler, I got a question to do with symmetry and the density. I know when I've been doing calculations, I've occasionally sort of used the lack of symmetry in my, or not all the symmetries being present in my sampled density as essentially a convergence check to tell me that I need to run longer. But of course, that's also something that we can potentially enforce. So do the tools know about symmetries, or is that something that people would need to apply themselves? So for example, in that water molecule, obviously there's a couple of mirror planes through the water.
So for instance, yes, you could, the tools don't generally use spatial symmetry, no. But one could write a short script that will sort of apply those symmetries yourself, and then you can, that's a good way to reduce your error bar. In terms of K points, the tools can use symmetrized K points. This is done just by providing, say, a set of XSF files, or sorry, H5 files to QDINs for each twist. And then you can also provide QDINs with, say, the appropriate weights. And so that at least can be used by the tool.